Mr. Sams?
No, it's Mr. Lewis.
Mr. Lewis.
Yeah, Meriwether Lewis.
Meriwether Lewis. Yeah, I've heard of him. He's like the Lewis and Clark guy.
Yeah, did some exploring.
So why are you wearing
early
Meriwether Lewis stuff?
Because we're talking about Lewis structures today.
Lewis structures?
Yeah.
Do you realize...
Lewis structures, didn't he like build some buildings like while he was out, build a cabin or two while he was exploring the
Wrong
Lewis structure?
Lewis, Mr. Sams.
Oh.
I think what you're thinking about is the other Lewis.
Oh. My mistake. I stand corrected.
I think what you're thinking, Mr. Sams, is of this Lewis. Right?
Okay, yeah.
Yeah, but we're actually I think we're going to be learning about what Mr. Gilbert Lewis did.
Oh.
The uber smart scientist guy that you obviously must not be. You know, because this is the real Lewis of the Lewis dot structure.
I'm a history major. What can you...
That must be your problem. Yes, well, he is a part of history. Gilbert Lewis.
Okay.
Science history. You must have your subject matters backwards.
Yeah.
Okay.
What can you do?
All right. We're in section 8.5 of your textbook, ladies and gentlemen. How do you like my southern accent? I've been working on it all day.
Well, it's better than nondescript Irish, Russian, Scottish, French.
What you talking about?
Yeah, that one.
Yes, okay. Hey, we're going to learn about the 8.5. Okay, textbook, Zumdahl textbook, if you're trying to figure this out. We'll talk about Lewis stuff later. All right, we're talking about how we form ionic compounds. So, you know, in that whole chart about different types of bonds, we're going to focus now for a little bit on ionic compounds. Now, recall, ionic bonds is a bond between a metal and a nonmetal. Right?
Yep.
And so we're going to look at the energies associated with this. There's this new thing that you haven't learned about. It's called the
lattice
energy. Lattice energy. And that's the energy that's found in a lattice. Duh. Yeah. Right? And it is the reaction of the metal in the gaseous state plus the anion in the gaseous state to make the metal. So this is the energy that's released as the ions bond.
Yeah. Now, does that mean it's always negative?
It actually is always negative.
Okay.
Lattice energies are always negative because they always release energy. Some are more negative than others, you know. And so when we talk about a high lattice energy, we're actually talking about a high negative value. So it's actually a lower one if you think about it. But energy,
larger quantity of energy going
because
up.
it's important to understand that there is no such thing as negative energy. That doesn't exist. But the negative sign just tells you the direction of flow.
Right.
So exothermics are negative and endothermics are positive. So this is always exothermic.
Yeah.
Okay? So hopefully that kind of figures. And it applies to something we've learned before. If you recall, the lattice energy equation, or this is actually Coulomb's law. You know, actually, I think we did Coulomb's law on that last time, and I think we were doing more of lattice energy equation, because Coulomb's law has an R squared in there, because that's a force. Yeah, we did it wrong. But it's basically the same concept here. Energy just doesn't have an R. It has R on the bottom. So where Q1 is the charge of, say, the sodium ion. We kind of talked about this before. And the chloride ion, say, if you're putting sodium with chloride, the Q1 would be positive 1, and the Q2 would be negative 1. And R is the distance between the atoms. Okay? All right, so let's kind of talk about how we would do this. These types of problems can get kind of crazy. And it really, I think, has been a confusing thing. It's not so terribly difficult. All right, there are some steps to make this happen. So you start with the metal and its standard state, and then the anion in its standard state, and then each step requires energy. And then we're going to try and make lithium fluoride. So we're going to form lithium fluoride. There it is. I think I need a blank screen for this. So we're going to form some lithium fluoride. So watch as I go through this step by step. All right. If I have lithium metal in a solid state, that's its standard state, and I want to turn it, first of all, to a gas. All right.
You're going to have to put some energy in to do that.
That's going to require some energy.
Yep.
And this, by the way, is called the heat of sublimation. Because if you turn something from a solid to a gas, then you will sublimate it.
Yes.
That's just kind of the definition. Now, we have a particular table in your book. If you're using the 6th edition of Zumdahl, it's page 363. But this requires 161 kilojoules of energy. All right. And then if I take the lithium as a gas, and I turn it into the lithium ion as a gas, that will release 1 electron. Now, we already learned about what that's called.
Ionization energy.
A couple of podcasts ago. That's an ionization energy. That's the energy of the lithium, and that has a particular value.
520.
And 520. Where we're getting these numbers just from a table in your book. Now you'll see I'll stop with that. Now I'm going to take the fluoride, but I'm going to take, when you take fluorine, by itself, it's a gas, and it always exists as F2.
Yep.
I want to then turn that into F.
Let's just make that half an F2.
Yeah, see, that's like a half an F2. Yeah, because I want to basically break the bond. What I'm doing, folks, is I have the FF, that sounds odd, the FF bond, and I'm trying to break this bond. And when we put the half, like we did in this reaction, we're taking a half of a mole of it. That's no negative sign there. And that would be called, this is called, and we'll learn about this in this podcast, actually, that's called the bond energy. And that value is
77.
So these are all endothermic reactions. They all require some energy. All right, but then we have another system. I can take my F gas and I can turn it into F negative. And actually, you'd have to add 1 electron on that side. And we've learned about this too. This is called the electron affinity. Remember, he wants to gain electrons. Now recall we said this, when this occurs, it's always negative because he releases energy.
320.
And this is negative 328. You know, we forgot to do something, Mr. Sams. On this bond energy one, we needed to multiply this 77 by 1/2.
Actually, the value in the book is given for
Oh, okay. If they give you the full bond energy and they have to cut it in half, usually that's 77.
Yeah, the full bond energy is 154 kilojoules.
All right.
So in this case,
actually, let's do it that way. Let's say this is 154, and we'll times that by 1/2, which gives us the 77.
Yeah.
And now, lastly, we can use our lattice energy equation, Li positive gas plus F negative gas makes LiF solid. This is called the lattice energy. We'll call it Le. And that value is usually quite large and negative. It's negative 1,047 kilojoules. Now, the good news about what you get here is we can now do some cancelizations. So I can cancelizations.
The electrons go away.
The electrons here go away. I see the lithium gas goes away.
Yep. Li plus goes away.
So you have Li positive here, and you have Li positive here, so they go away.
And the F minuses go away.
F minus is here.
Right below.
And this is on the same opposite side. It doesn't look that well. And I think the F gas.
Yeah, F gas goes away. Yep.
With what?
The other F gas.
F gas here. So what are you left with? You're left with Li solid plus 1/2 F2 gas makes LiF solid.
Right, so that's the overall reaction of taking solid lithium, gaseous fluorine, and making lithium fluoride.
And if you add all these numbers up,
negative 617.
You get negative 617 or 617 kilojoules per mole. So if you know your steps, you have to know each of the steps. First of all, I took the metal and I sublimated it. Then I ionized it. And then I was done. And then with the fluoride, I broke the bond, and then I ionized it. And then I added it all up, and that's how you do this. These aren't terribly difficult. Here's a better picture of it here. The first step is I took the lithium, and I sublimated it here. As you can see, the solid turned into a gas. That's the only thing that changed. In the second step, it required me to ionize it. I turned the lithium into lithium positive. In the next step, I broke the bond, F2, and made F, right? So the F2 turned into F. And then we added the lattice energy, and then it all canceled out. Oh, this is the electron affinity. I'm a step ahead. This is the electron affinity, and then this right here is the lattice energy, and the overall change was a negative, so this is an exothermic. So if you take lithium and you react it with fluorine, half of these, you will get quite an exothermic reaction. It could probably explode even, so pretty cool to see. All right. Now, you might remember back in chapter, what was that, 16? 5 even, we talked about how to find delta H. We learned there are 4 ways to calculate delta H. Hess's law version 1, products minus reactants. Hess's law version 2, add the reaction method. We kind of did that.
Kind of just did,
yeah. And then third one was calorimetry. Yep. Remember delta G, or delta H will be kilojoules divided by, you do Q equals MC delta T, and then you do your moles. And I've always said that there's always one more method.
Yep.
And that method is called bond energies.
Here it is.
And today you're going to learn how to use bond energies to find delta H.
Yep.
And here's the key reaction, or equation. It's bonds broken, bonds formed. Now, something that's about odd this, if I've got, A plus B makes C plus D or whatever in some reaction, the bonds broken are from the reactant side. So notice I said reactant bonds minus the bonds on the product side. And the reason that's kind of weird is you're pretty used to taking products minus reactants. But if this one, you're going to go
reactants minus
reactants
products.
minus
It's the
products.
only one of them that you do reactants minus products.
So it's a little bit weird.
Yep.
Okay.
That's why I always just think the broken minus form thing.
Yeah, broken minus formed. Now, you break things on the left and you form them on the right. Now, something we haven't really learned too much how to do, so we're going to do a really quick introduction on organic chemistry so that you can draw the bonds. A lot of students struggle with this. If you've got a halide, what's a halide? What's that mean?
It's an ion from a halide.
So it's fluorine, chlorine, bromine. It's the last column on the periodic table, well, second to last, I should say. That's not including the noble gases. Plus hydrogen, they basically need one bond. Oxygen and sulfur on the periodic table need 2. Nitrogen and phosphorus need 3, and carbon needs 4. You'll see why that's important in just a minute. Okay, so let's do an example. Actually, this is a table, so if you open your book to page, I don't know what page it's on, Mr. Sam.
Oh, boy, I don't know, 8.4. Let me find it.
Yeah, well, anyways, you've got this table, and you'll need to use it big time on your podcast, on your notes. There it is, page 372.
Yep.
And this is the bond energy. So if I've got an HH bond, it has an average bond energy of 432 kilojoules per mole, or if it's IBr, it's 175, or whatever the case might be. There's a special case, by the way, down here. In the carbon dioxide, the double bond is 799, whereas normally it's 745. So it's sort of a special case. Okay? And then also we have bond energies of some other selected bonds. Okay? Now, it says calculate the delta H for the following reaction. Now the key thing when you do this is that you actually have to know what bonds hold it together.
Mm-hmm.
Now remember I said that carbon, I have to actually draw the structure. So
Yep.
carbon normally needs 4 bonds. And so if I've got 4, and hydrogens want 1, so when I do CH4, I have to draw this out like this. Plus the chlorine. Now chlorine is a halogen, so he needs 1 bond, so I put another chlorine. But there are 2 chlorines here, so I'm going to say chlorine, chlorine. You see that now?
Yep.
Because there are 2, and then I got 2 fluorines, and he's also F, F, and then F, and then F. And he's going to make a CF2Cl2. So carbon wants 4 bonds, and if you see that there's 2 Fs and 2 Cls. So it's going to look like this. Okay. Plus an HF, which is H, just F. Everybody wants 1 bond in this case.
2 of those.
Oh, and you want 2 of those, that's correct. And you want 2 HCls. Got it? Now, here's the key. These bonds over here will be broken, and these over here will be formed.
Yeah, so we're breaking them up, rearranging them, and sticking them back together.
So if I have the CH4 bonds, what I would actually do, I wish I could go down. Well, we'll just do it right here. All right, I'm going to have 4 CH bonds right here. Now, that means I'll take 4 of them times the value of a CH bond.
413 each.
Some 413. And then I've got 2 Cl bonds, so 2 of those.
Times 239 each.
239. Actually, you don't have to put the 2 right there, I guess. And then I have F bonds, and there are 2 of those, and that's going to be
154
154 each.
And that's a total of 2438.
2,438. This second one over here, I've got a CF bond. I have 2 of those.
And those are 485 each.
485. And I've got a CCl bond, and I've got 2 of those.
339 each.
339. Folks, you understand where he's getting that. He's using this table right here. Got it? Okay. And then I've got HF bond, and there are 2 of those.
565 each.
565. And I've got an HCl bond, and that's 2 of those. 427. So if you take and add all these numbers up right here, 2 times 485 plus 2 times 339, et cetera, et cetera, et cetera, you get the grand total of
3632.
3632. And it's bonds broken minus formed. So then you're going to take the 2,438 number and subtract 3,632, and you get a negative answer.
Yep, negative 1194 kilojoules.
That is the delta H for this reaction.
Yep.
Bonds broken minus bonds formed. Let's do one that's just a tad bit more complex. So it's N2O4. All right, I'm going to get a blank screen. N2O4. So it's going to be in. Is this right? O. Are the N's in the middle?
Yeah, I believe they are. And that's the rocket fuel one, right?
The N's want 3 bonds, but the O's want 2. So this isn't going to make them happy, Mr. Sams.
We're going to have to draw this. Are those double bonds? No, can't be double bonds.
That's what I was thinking. Unless it's N-O-N-O-N-O. It's got to be this.
I forget. Let me look it up.
Well, let's pretend that it is. Okay? So we've got N2O4, but there's 5 of them. I'm just going to put a 5 right here. And we're going to make N2H3CH3. So you got to figure out how to draw this. N2H3 CH3. Yeah, it's going to go look like this. Oh, okay. Like that, Mr. Sams?
Yep.
Okay, I messed up. Okay, but this I'm good on this one. This is actually violating the in rule, isn't it? You usually
that would
want
probably be
3 bonds.
given to you since it's a weird one.
Yeah. All right.
We had to look it up in here.
And there are 4 of these. And that's going to make 12 waters. Water, of course, is just HOH. And there's 12 of those. Plus 9 nitrogens. Nitrogen has a triple bond holding it together because he needs 3 bonds, generally speaking. And carbon dioxide he needs 4. And the only way to really make everybody happy is to do it to double bond. Wrong direction. And that's 4 of those. So now we're going to sort of total everything up.
All right.
All right, I've got N bonds.
N bonds.
And I have 5 of them.
Single N bonds?
Yes.
Okay, single N bonds, 160 each.
160 each. Now,
Okay.
that's this bond here. Now I've got N double bond O. Now I've got 5 molecules of this, but I've got 2 per, so I've got 10 of them, if you think
Yep.
about it. And how much is that?
607.
607. And then I've got the N single bond O, and I will also have 10 of those.
201.
201. Now, that's the first molecule. The second molecule, I've got some N bonds. I guess we've already done that, but
Yep.
we have 1 of them per molecule and 4 molecules. So actually, let's just change this to a 9, right? 5
right.
plus 4 is 9.
I'm good with that.
So let's call this NH. We've got quite a few NHs. I've got 1, 2, 3 of those times 4, so I have 12 NH bonds.
391 each.
391, and then I've got, which am I missing? I've got an NC bond, and I've got 1 of those. That's this bond right here. So 4 of those. What's an NC bond?
305.
305. And again, we're using that same chart, folks. And it looks like I've got some CH bonds. I've got 3 of them, but 4. There's 4 molecules, so that'll be a 12 banger. And that's
CH
4
is
something?
413.
413. So then we take all these and we add them all up.
And I'm frantically putting that in my calculator right now.
All right.
We got 20388.
20,388. Now on the other reverse side, we've got 12 waters, so I've got an HO bond, but there are 2 of them here, so that'll be 24 times, what's the HO bond?
467.
467. That'll be a big number. For the triple bond, the N triple bond N, there are 9 of them, and that's a big number.
941.
941. And then the C double bond O for the carbon dioxide, there are
Oh, this
2,
is the special case one.
8. So the 8 of these, isn't that 799?
It is.
Yeah, times 799. Not as many, but still they're going to add up a pretty big number. So what does this add up to, Mr. Sam?
26069.
Okay, so what do you do now?
Products minus reactions.
Products minus reactions. 20,388 minus 26,069, about negative 5 grand. Something?
Negative 5681. Nicely exothermic.
Yeah, very exothermic reaction. There you go. I think this is like a rocket fuel problem, actually.
Yeah, I think it is.
So it better be exothermic. That's really, really exothermic. Negative 5,600. Yeah, so I could believe rocket fuel on that one. All right. Let's we do this, Mr. Sims? I think, guys, we're going to skip this question. Mr. Sims, I just had a discussion off camera. So, good news. Skip. All right. Oh, Lewis!
Yes.
Mr. Lewis.
Yes,
all right.
Mr. Clark.
No, Gilbert. We got back to Gilbert finally. How do you do Lewis structures? All right. There's the octet rule. You need to copy these rules down. If you've done Lewis structures before, you can. So pause the video and copy these things down. And now we're going to do a bunch of examples. All right. So how do I draw a Lewis structure? Now we're talking now only about Lewis structures of covalent compounds. So let's do a molecule like say SO2. All right, the first thing you do is you count the total number of valence electrons. You know, that's something, did we talk about how they know how many valence electrons there are?
Let's throw a periodic table on there and show them.
I think we probably should do that. So if we have a periodic table here, the number of Lewis, or the number of valence electrons, column 1 is 1, 2, 3, 4, 5, 6, 7, and 8. So if you have a periodic table out, you should get it out. And we don't really mess with these guys in the middle.
No.
And we're talking about covalent compounds. So essentially we're only talking about the elements in this box here. I didn't draw a very good box, plus hydrogen. So, yeah. So let's go back to our example of SO2. For SO2, sulfur, if you look here, he is in column, the 6th one, so he gets 6, and so is oxygen, by the way.
Yep.
So they're going to have 6 plus 2 times 6. Or 6 times 3, 18 electrons. So you always start with your central atom, which is the S in this case.
And usually that's the element that's written first. That's the one that goes in the middle.
And so you go 2, 4, and then and bonds, which we said in the rules, bonds count as 2 electrons, and double bonds count as 4. So we're going to distribute the electrons so that everybody gets 8 electrons. So I've spent 4 of my 18. So 4, 6, oh, pardon me, I don't want to do that. You do the last that first.
Yep.
6, 8, 10, 12, 14, 16.
And then 2 on the middle.
Yeah, I need to spend 2 more so they go in the middle.
Yeah.
Now,
you do the outside ones first, and then you put your extras in the middle.
Now, the problem with this picture, of course, is that everybody has 8, right?
Sulfur doesn't have 8.
Sulfur only has 6. So to fix this problem, I have to erase 2 from one of the oxygens, it doesn't matter which, and I make a double bond.
Yep.
So that is the correct Lewis structure of SO2. All right. Let's do an ion. Let's say NO3 negative 1. Now, if you look back at the chart, nitrogen gets 5, right? So we'll put 5 for nitrogen plus 3 times 6 for oxygen. Now, what do you do with that extra charge, Mr. Sanders?
It's a negative charge, so we get an extra electron to work
So
with.
negative charges have extra electrons. Positive would be less electrons. So 18, 19, I think that's 24 electrons. Yeah, it is. And so if I draw the Lewis structure of this, I'll do N, and I'll put my O's around it. And I'll say 2, 4, 6. And then 8, 10, 12, 14, 16, 18. 20, 22, 24.
Nitrogen
Is still unhappy. So I have to erase 2 electrons arbitrarily from this bottom left-hand corner one and make a double bond. Now I've just redistributed the electrons. Now because it's an ion, I do have to put brackets around it. I have to put a charge of negative 1 right there. If it doesn't have a charge, you don't have to put the brackets, but you do in this case. All right, how about we do another one?
Should we do a big hairy one where it goes over the...
That's later on, actually, when we
Okay.
do exceptions.
Okay.
Let's do...
How
how about
carbon dioxide?
Carbon dioxide. All right, carbon gets 4 electrons, plus oxygen gets 2 times 6. So that's 12 and 4 is 16. So you're going to have carbon, oxygen, oxygen. So 2, 4, 6, 8, 10, 12, 14, 16. So it works out perfect. Not really. The carbon's unhappy. So what do I do?
Steal 2?
Steal 2. Is carbon happy?
Nope.
No, so I steal 2 more. Now, technically, I could have taken them both from 1 and made a triple bond, but you try to distribute it as much as possible, with some exceptions that we'll learn about later. Okay? So you're going to draw so many Lewis structures, you're going to get sick of them.
Yes.
Ad
nauseum.
Now, that always assumes that you want 8. There
Yeah.
are what we call exceptions to the octet rule. And so, basically, we follow the same set of rules. We just have a few exceptions.
Yes.
So why don't we do PCl5?
Ooh, that's a good one.
All right, let's do PCl5. So P is 5, plus chlorine is 7s, so it'd be 5 times 7. So that's 40, right?
Yep.
So if I've got P and Cl, 2, 4, 6, 8, 10. First of all, I've already spent 10 electrons. That's over the 8 number, isn't it?
Yep.
So that's just it. It's
That's
okay.
the only place you can put them. So
You've got, yeah, so we spent 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40.
All the chlorines look happy. They all have 8.
And everyone's happy except for the P, and he just, there's no way to make it work. So he's considered an exception to the octet
and P
rule.
can go over. Actually, anything in the third period or below can actually go over the octet rule.
Yeah, so basically guys from here on out, and really it's these guys, pardon me, here, these guys can go over. Boron and carbon and nitrogen, they cannot go over.
Nope. Do they need to know why?
Later on, I think we'll talk about
Okay.
why. Yeah, that's a good point. We do, yeah, it's later. All right, let's do another one. Let's do, let's do ICl4 negative. There's a wild one. ICl4 with a -1 charge.
It's an
Iodine,
ion I don't want to encounter.
I don't think so either. Iodine has 7,
Yeah.
plus there are 4 chlorines, and that's 7.
7.
Plus we get 1 more bonus because of the extra electrons. So
Yep.
7 to 35, is that 36?
36.
I got 36 electrons to spin. So the central atom will be iodine. And I've got 4 chlorines. So 2, 4, 6, 8. Who do we oh, that's something else. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I got 4 more.
You got to stick them in the middle.
33, 34, 35, 36. And since it's an ion, we put a bracket around it, we put a
Charge.
-1 charge in this case. Now, how many electrons are in each chlorine?
8.
8. So they're happy. Iodine, though, has 12.
12.
And that's okay.
Yeah.
So it's an exception to the octet rule.
Yep.
Okay? So, folks, that's how we do this. A lot of procedural stuff on this particular podcast. I think you just need to, you're going to get lots of practice in class and in your homework and da-da-da. So keep working, and we will help you later. Have happy days. Bye.
Bah.